Rates of change. Bring on the excitement. All right. And remember, there is a few things going on with rates of change. Okay, we've talked about two different rates of change. We talked about the average rate of change and the instantaneous rate of change and the difference between the two. Okay, what we're going to mainly focus on today is dealing with the free fall equation. Okay, so we're going to do some physics action. But that means all you kids that were experts in physics last year, or if you're currently in physics, we want to use the calculus stuff to actually answer some of these questions instead of what you guys are doing in your physics class and some of those equations that you guys memorize. Okay, so we are going to talk about rates of change, and remember there's two of them. We had average rate of change, instantaneous rate of change, but what I want to focus on is the position equation. Okay, so first of all, anything that moves has a rate of change. Okay, if you're traveling in a car, the car has speed, it has acceleration, it has direction, forward, reverse. So we have velocity there. If you're running, again, you're running at a certain speed, you accelerate, you decelerate. Same with walking. So anything that moves has a rate of change, and we want to just use that in order to calculate rates of change in certain situations that we're going to see in this class. So remember that we have two rates of change. I have the average rate of change, which was the slope between 2 points. Slope of the secant line. Remember, here I needed 2 points to calculate the slope. The other one was the instantaneous rate of change. Let's spell out instantaneous. Instantaneous rate of change. Remember, this is the slope of tangent line. And we are talking about 1 point. All right, so that is what we have going on there, just talking about 1 point. So if we are going through those things, okay, it is just using this idea to help us answer some questions as we're going along. So what we want to focus on today is going to be the position function. Okay, so we're going to focus on the use of the position function. Okay, so the position function is S of t is 1/2 gt squared plus v initial t plus s initial. That is going to be the position function that we're going to use. Okay. So all you physics kids are probably dealing with meters per second and things like that, but we're not physics kids, we're like calculus kids. So we are going on thinking about this right here, okay, where this is going to be t, okay, remember, and that is going to be time. And then this is going to be s of t, remember this is position. Okay, that got a little messy. I'll write it a little bit bigger. So that is going to be position. All right. So typically when we think about time, and here we're usually dealing with seconds. Okay, so time, we're going to deal with seconds. And typically position, we're going to deal with feet. All right, so not necessarily meters, but we're dealing with feet. So anything I have that I'm calculating a rate of change, we're going to be looking at, slope, and then figuring out the units for that. So if I have some kind of graph, okay, and if I want the rate of change of this graph, okay, so if I'm taking a look at this, if I'm taking a look at any rate of change for this graph, it is going to be my change in y over my change in x. So the rate of change, the units for this are going to be feet per second if I'm talking my position in feet and my time in seconds. So the rate of change, remember, is the slope. Slope is change in y over change in x. So here, my y values are measured in feet, my x values are measured in seconds. So what we're looking at is we're looking at units that are going to be feet per second. All right, since we're dealing with feet per second, that means this gravity right there is going to be negative 32. So not that negative 9.8 that you guys are used to in physics, that meters, per second squared. So this is going to be a negative 32 because we are talking feet. So what we usually deal with is this, negative 16 t squared plus v initial t plus s initial. And this is going to be my position s of t. Okay, so boom, 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 boom. And the reason it's negative 32 is because it is feet per second squared. Gravity is negative 32 feet per second squared. So that's where I get this, negative 16 t squared plus v initial t plus s initial. Okay, so a few things to remember is that this part right here, am I going too fast? Are we okay? We're good, we're good? All right. So this part right here is my position at time t. So that's my position. Sometimes books will refer to it as x of t. Okay, so x of t will also be that, but we're just going to keep with s of t going with the textbook on this one. V of 0 or v naught is going to be my initial velocity. And then this s naught is going to be my initial position. Okay. So those are going to be things that are going to be changing throughout. Okay. So some things to think about with initial velocity. Okay. Is it dropped? Is it thrown? Okay. So these are things to think about with my initial velocity. Dropped, my initial velocity would be 0. Thrown, it would be something else. Okay. Initial position, let's think about, are we on a building? Okay. Are we on ground level? Okay. So these are just things to think about when we're working with those problems. Not everybody has been through physics or wants to take physics, or maybe you're currently in it and haven't talked about these things yet. So this is just some things to think about in this class when we deal with these problems, okay? So what we're going to do is, in order to use this equation and show the types of problems we're going to deal with, is we're going to do one problem out of the book and just kind of use that as notes. So we're going to use this equation, all of this information. Remember, this is just a position function. This function, I can calculate an average rate of change, or I can calculate an instantaneous rate of change. And my units for that rate of change, if I'm dealing with feet on the y-axis and seconds on the x-axis, remember, slope is change in y over change in x. So I'd be looking at feet per second when we're talking about those things. All right, so if you want to make your life a little bit easier, it is page 137, number 99. So if you have your book in front of you and you just want to be able to reference the question, it's page 137, number 99. So this is, all right, so that is going to be the problem we're going to do. I am going to insert it and just talk about this problem, just parts of it. So I am, whoa, where'd you go? There we go. So this is going to be the problem, but I'm not going to leave the entire thing up here. I'm just going to crop to it and deal with just one question at a time. So now we're just going to deal with number 99, part A. Okay. So there it is. I'd try and make it a little bit bigger so you can see it a little better. Hopefully that is good for you guys. Okay. So remember the equation that we're using. I'll let you copy this down. Okay, but we have a few things. I have this equation, S of t, equals negative 16t squared plus v initial t plus s initial. So I have that, okay? And going through, I know a few things about this problem by how the first part of the question is stated, okay? All right, I'll give you a second to catch up. All right, so a few things to think about, all right? If I take a look at this, a silver dollar is dropped. That tells me that my initial velocity, v of 0, which is my initial velocity, okay, is going to equal 0. All right, since it's dropped. If I take a look at this part, that is from the top of a building, 1,362 feet tall, that tells me that my initial position, s of 0, all right, is going to be 1,362 because I'm at the top of that building, okay? So when I set up and I use this equation and I plug those things in, okay, remember that v of 0, okay, is going to be that 0 value, and then that s of 0 is going to be the 1362. So I'm just plugging those numbers in, and what I'm going to get then is this equation. S of t is going to be negative 16t squared plus 0t plus 1,362. So S of t is going to be negative 16t squared plus 1,362. Okay, that is my equation. So what I always want you to remember is what are the units that we're dealing with. I'm not sure what this graph looks like. I really don't care right now. I just care about the units. I know that the units for this, t right here, is going to be seconds. And S of t right here is going to be feet. So that's what I care about. I don't even know what the graph looks like. I could graph it out and do that, but right now I don't care. I just want to know that this problem is giving me these units so that when I calculate a rate of change, remember, rate of change, so whatever this graph looks like, any rate of change that I calculate is going to be the change in y over the change in x. So that is going to be feet per second. So anytime I'm calculating a rate of change for this problem, it's going to be feet per second, because that's what rate of change is. It means my slope, which is my y values measured in feet over my x values in seconds. So anytime I'm going to calculate a velocity in this case, well, that is what we're dealing with here, okay? All right, so now I want to determine the position function, which I did. Remember, this right here is position. So my position is definitely right there. And now I want to calculate the velocity function, okay? Well, velocity is the rate of change of position. So in order to do that, velocity is going to equal the derivative of position, which in this case is going to be the power rule, negative 32t. So my velocity equation is going to be negative 32t, and that is going to be the velocity function, and I get that by taking the derivative, because remember, the derivative gives me rates of change. I want the function, so I'm taking the derivative. So I'm just using the power rule to calculate that. So that is part A right there. I have my position function, I have my velocity function, and how I calculated those, okay? So remember that S of t is my position, and then what this is, velocity, this refers to the velocity at time t, okay? So remember, this is the instantaneous. All right, so that's what we have there. It's the instantaneous going through. All right, so cruising right along. That was part A. Now I got this on the video, and I'll also throw these notes into our Schoology. Questions on part A? Can I move on to part B? So I'm going to scroll down then. I'm going to move this off the screen. And I want to get part B on there. So again, I'm going to drop part B in. Boom, boom. Let's put it right here. All right, so there we go. And I just want to deal with part B right now. So I want to determine the average velocity on that interval. All right, so this is part B, determine the average velocity on the interval. Now remember what average velocity is. Average velocity, as we stated earlier up here, okay, was the slope of the secant line. I have 2 points, okay? So if I'm going through, I need 2 points. So this right here, okay, this 2 points was f of b minus f of a over b minus a. So that was that average velocity that we talked about last chapter when we talked about differentiation. So the average rate of change, then the limit process brings those points closer together, which will give me the instantaneous rate of change. So whenever I see the word average velocity or average rate of change, I'm using f of b minus f of a over b minus a. So in this example down here, I want to determine the average velocity, okay? So this is going to be that f of b minus f of a over b minus a, but in this case, it's going to be s of b minus s of a over b minus a, okay? Now remember, you want your final answer to be velocity, and velocity is measured in feet per second. So if velocity is measured in feet per second, I got to make sure that the top here, this is measured in feet and this is measured in seconds. If I were to use my velocity equation, that wouldn't give me a final answer of feet per second. So make sure if I want average velocity that the top part of the fraction will be measured in feet and the bottom is measured in seconds. So if I'm going through this then, in order to calculate it out, it is going to be s of 2 minus s of 1 over 2 minus 1. So all I'm doing is I'm taking that position function that we calculated, it's off screen now, but it's negative 16t squared plus 1362, I want to say. Yeah, plus 1362. So this is what I want to calculate. Okay, so this, okay, average velocity. And so remember, I'm just going to write this for note purposes. The top is my change in position over those 2 points over my change in time. Because that's what a rate of change is, my change in position over change in time. In this case, okay, we could have other rates of change that measure other things. Okay. So this is where I just plug in my calculator. I know that s of 2 is going to be negative 16 times 2 squared plus 1362. So that's going to be 4 times the negative, so that's going to be a 1298. I know that s of 1 is a negative 16 times 1 squared plus 1362, so that's going to give me a 1346. And now I'm just plugging these numbers up here. So it is 1298 minus 1346 all over 2 minus 1. So I'm just calculating out those numbers, okay? And what it's going to give me, it's going to give me a negative 48. And remember, you need to know units in these situations. So in this situation, what we said earlier, according to this graph right here, was that change in position was feet, change in time was seconds, so it gives me feet per second. So that is what I get right here as in feet per second. All right, so that is letter B. I'll leave it on the screen. I'll put on letter C, and we will, boom, get to it. Bam, bam, bam. Crop it. And there we go. So here is letter C coming at you. Okay. So a key word right here. Are we cool to go on? Still on the screen. Gonna move it up a little bit. Thank you, thank you. Appreciate the thumbs up. So if I want to calculate in this case, keyword is instantaneous velocity. So that means I am using S prime of t, which equals v of t, because that's the keyword and instantaneous. So anytime I see at a time or instantaneous, if it, it says it right there, that means I'm going to use this equation that we calculated earlier, negative 32t. So this one, pretty straightforward, okay? I am using v of t is negative 32t. So v of 1 is negative 32 times 1, which is a negative 32. V of 2 is a negative 32 times 2, so that's going to be a negative 64. And then it's remembering that these have units, and those units are rates of change or velocities. And in this case, again, that graph up top, feet per second. So this, feet per second, feet per second, okay? So just going through and calculating those. So it's going through and knowing what to use. Am I using the position equation to find the average rate of change? Using the velocity equation to find the instantaneous rate of change? And how I calculated the velocity equation by taking a derivative. Okay, so here we go. Letter D coming at you. Dun, 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 dun. I'll put it on this page. So insert image. Let's go this one. We'll go right here. Stay over it. Oh, stay over. Come back to me. Crop. And croppity cropping. Croppity cropping. Boom. Oh, wait. No, stay there. And bam. Here we go. Letter D. Find the time required for the coin to reach ground level. All right. So remember what we're finding here. Okay. So finding time. So here it is. I am find the time required. That means I'm gonna find t. So my final answer should be something that t equals. Okay, it's not gonna be anything else. It's gonna be t equals. And since I know that we're finding a time, I know in this problem, it's gonna be measured in seconds. Okay, so I know the units of this already. I'm finding time and it's measured in seconds. I can put all these things together, okay? And another thing, for the coin to reach ground level, okay? That means that my position is 0. At ground level, I'm at 0 position. So remember, my position is S of t. I want to find when that equals 0. So this right here is how we're going to go ahead and solve this just by what the problem says. I'm finding when my position equals 0. So basically, going through what we did earlier, remember, S of t was negative 16t squared plus 1,362. I want to find when it equals 0. So if I want to find when it equals 0, I just do negative 16t squared plus 1362 equals 0, and then I solve it out. Welcome to algebra. Yay, you guys, this is easy stuff. Zero calculus going on. Okay, I have a position equation. I want to find when that position equals 0. So set it equals, solve it out. Just plug some things in the old calculadora, the Explorer, hit enter, and you're good to go. Okay, so I'm sure you guys can do this. Negative 16t squared equals a negative 1362. Eventually, t is going to be 9.226 seconds. All right, remember, it is measured in seconds. There you go. Okay. So I'm thinking you guys can solve that out. I didn't want to steal your thunder if you really wanted to solve it out and use a calculator this morning, but there it is. Okay, 9.226, 3 decimal places. Okay, so 3 decimal places, going through that, and just making sure I calculate that out correctly. But look for the key words. I'm finding time, so I'm going to find t, and when it reaches ground level. Okay, so make sure you know what you're finding. A lot of kids are just writing down numbers and they have no clue what they mean. Numbers have meaning. All right, and then here it is, part E. All right, so throwing in a picture, boom, and padow, right there. We will croppity crop it, bam, going all the way down, boom, and find the velocity of the coin at impact. All right, so I know that I am finding velocity. Okay, so I am finding velocity. Okay, velocity, and then I want to find it at impact. So at impact, when it hits the ground. All right, so at impact. Well, remember, in order to calculate velocity, I have to know a time. That's why it's written v of t, okay? So when it hits the ground, I know it's 9.226 seconds. That's the time it takes to hit the ground. We just calculated that. Well, I want to calculate velocity. Go away. All right, I want to calculate velocity at that time. So I just want to figure out velocity at 9.226 seconds. But remember from earlier, velocity was, what was it, a negative 32t? So that was my velocity equation. Well, I just want to calculate negative 32 times 9.226. And that will tell you my velocity at impact, okay? And if I take that and multiply it out again, I know you guys can use calculators. This is going to be a negative 295.242. You should know the units because it's velocity. We talked about this is going to be feet per second at impact. Now, the reason I'm using my velocity equation, my derivative, is the key word at. It's at an instant, instantaneous. So at that time, that is how I calculate it out. Okay, it wasn't like earlier I wanted the average velocity. So there we go.